Okay, so good morning, Lydia, and good afternoon, everyone. Today we are going to have a very special invited speaker. So the speaker today is Dr. Lidia Fernández from Universidad de Granada. Is my pronunciation correct or not? So University of Granada from Spain. But before we start, we would like to invite Professor Alhadi Bustamam as head of mathematics department to give a welcoming speech. Professor Alhadi, please.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirabbil alamin. Assalatu wassalamu ala Rasulillahi sayyidina Muhammadin wa alihi wasallam. Good morning, good afternoon. Good afternoon, Prof. Lidia Fernández, and also for all the participants, and also our colleagues from Faculty of Mathematics and Natural Science, University Indonesia. We are very happy to welcoming you in this series of seminar. This seminar is the MIPAtalk Series that have been conducted since 2019, since COVID-19. So the first talk is about COVID-19, and one of the series is at that time I was the speaker about the COVID-19. First of all, please let introduce myself. My name is Alhadi Bustamam. I'm the head of the Department of Mathematics. My background in computational mathematics, especially in data science, bioinformatics, and also artificial intelligence research focus. And I'm also the chair of data science center in in our faculty. So we are have a very great honor because we get the distinguished speaker from Spain, yeah. And I checked using Google Translate, and you are from the Department of Applied Mathematics. So I am wondering, is there any other department? So, and we get the information from you that there are several a specific department related to mathematics in your faculty. In our department, we have like a study program, actually mathematics, statistics, actual science in bachelor level, and also we get like postgraduate program in mathematics for master degree. And inside this class study program, like in mathematics and in postgraduate program, we get like research focus, like theoretical mathematics, computational mathematics, data science, and also modeling and applied mathematics. So we get the topics is very familiar to us, orthogonal and polynomial, because all of our students already study this in linear algebra. But when we read your abstract, it's make me like, wow, this is pretty hard to me. So I hope we can get a lot of new insight from you about this topic. And this is one of the favorite topic, I think, in linear algebra. So I think this is this topic. I believe a lot of application in all of the area we study, like in statistics, in mathematics, in especially in data science. Yes, because the data science is derived from mathematical modeling, also in statistics as well. So we have you are very happy, and we are also very happy to welcoming you here, and we hope in the future you can visit us offline. Yeah. Thank you for the committee, especially for the director of research and community engagement in our faculty to conduct this series. And in the name of God, we open this webinar. Thank you very much, Professor Lidia, and also for all the participants. Have a nice webinar today. And I will give that to Ibu Kiki. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Pak Alhadi, for like the welcoming speech. We already have some colleagues from other university. Here I see Pak Suciana from Gajah Mada University. Maybe Lidia already met him when you visit the UGM last time. And also we have Ibu Robiatul Adawiyah from Jember. And there are some of my colleagues from UI. We have, apart from Professor Alhadi, we have Bu Bevina, Pak Hengki, Bu Rahmi, and also Bu Yakti, and also some students and other names I don't remember students or colleagues from other university. So before we start, I would like to invite you to because we need to have pictures. Mbak Justin udah siap ya? Mbak Justin?
Iya Bu, silakan Bu.
Hello. Okay, so give your big smile. Ini yang motret siapa ya?
Saya aja Bu.
Okay.
For all the participants, please open your camera. There are only one slide.
Yeah, so this is a bonus for the people who come first.
We are still waiting for some people to open the camera ya Bu.
Ya, Bu Yakti.
Itu ada Ibnu Hadi itu, berarti anak saya itu ya. Anaknya Alhadi.
Oh iya.
Itu dari mana? Dari luar ya?
Oke, Mas Ibnu, Mbak Dian, Mbak Harina, Mbak Robiatul, could you please open your camera or Mas Faris?
Mas Faris nggak punya kamera Bu.
Oh nggak punya kamera, oke.
Okay, maybe we can start taking pictures in 1, 2, 3. Once more, 1, 2, 3. Okay, thank you Bu.
Okay, thank you Mbak Din. Oh sorry, why my slide is, sorry about that. So I start to have wait a minute. I lost the CV. So I would like to introduce Associate Professor Dr. Lidia Fernández. I hope you can see the slide. So she comes from the Department of Applied Mathematics, University of Granada. And the research interest is about applied math, numerical analysis, and orthogonal polynomials. That's the topic that she like to share with us. The interesting thing is the organization that she involved is quite a lot here. We have Real Sociedad Matematic Española, maybe it's Mathematics Society from the whole Spain. But there are some interesting a member of Orthonet. Orthonet is a special research group that the research is about orthogonal polynomials. So it's very specific. But this is also national in the Spain. And also she is the scientific officer of SIMPA. I think most of you already knows about SIMPA. That is the International Center of Pure Mathematics and Application. I will not what is read the French name for this, because like I will make sure that I make mistakes. This is like publication, the new publication of Lidia. So please, Associate Professor Dr. Lidia Fernández, she will give a little bit information about the SIMPA that is very interesting and a great opportunity for us to like can join that event. So Professor Lidia.
So thank you very much for invitation. The first thing I want to do is to thank all of you for inviting me to be here with you, and I want to thank all the people who is attending the conference, because I understand that it's very specific and that there is another one at the same time. So, well, the first thing I want to do is, I'm always that I give a talk, the first thing I do is to explain a little bit about SIMPA, because I think that is my compromise, with SIMPA to spread a little bit, because I think that people sometimes doesn't know the lot of things that they are doing for. So I'm going to share something with you. Let's see if it works. Page. So that's it. So SIMPA is a center that is a UNESCO category 2 center. So it is this main objective of this association is to promote the research in mathematics in developing countries. It was founded in 1978 and is based in Nice, but there are many countries involved in this organization, in particular Spain, that is where I am from. I am a scientific officer, so I am in general related with the schools, with the SIMPA schools, but there are other things that are organized by SIMPA, like the research in pairs, where people from developing countries are going to a country in Europe to work with somebody in something that they are interested in, or the SIMPA fellowships that are for young people who want to study abroad for some time, and there are some fellowships that are given by SIMPA every year. Of course, there are SIMPA courses online and on site, and schools in partnership, but the main thing I think the thing that moves more people is the SIMPA schools. That is where really I am more involved in this organization. So I want to explain a little bit how to organize a SIMPA school, and I want to encourage all of you to organize one of these schools in your country. Of course, I can help with everything that you need. So I don't know what happens here. So how can you organize a SIMPA school? The first thing that you have to know is that you need to be in contact with somebody in Spain, France, Germany, Norway, or Switzerland. So the first thing that you need is 2 people. One that is an external coordinator in France, Germany, Norway, Spain, and Switzerland, and a local coordinator in a developing country. Here, there is a picture of the last school in Yogyakarta, and the organizers, the coordinators of this school were Marusia, Rebolledo, and Unique. This is the picture of they both. But if you, for example, want to organize a school and you don't have a contact in France or Germany, I can help with this, as I said before. So the second step is to contact with a scientific officer. This is my work in this. So in this contact, you have to see, or you have to improve, or to focus on the relevance of the school for the country and for the region where it's going to be held this school. Second, the local impact of the project. And if it is going to be a long-term project, it's better, because the main objective is to make that people who are in the same country or countries in that are neighbor of this one establish relationships to work together in the future. And the third thing is to have a budget well prepared and to look for external fundings, because SIMPA is going to give you half of the money, but the other half of the money is coming from another institutions or the university in the country where it's organized and these kind of things. After you have a team with people who are going to teach in this school, here there are a lot of teachers that were in this school in Yogyakarta. Juni is there in the picture. And they have to look for the scientific and pedagogical qualities of the school. There has to be a gender balance. It's at least 30% of the people has to be men, and at least 30% of the people has to be women. And it's another important thing that there has to be local professors involved in the school too. So this is more or less the idea of how it works. But how are you going to do that in the time? So the first thing is to submit your proposal online, and this is between March and October. So now the call for project for 2024 is open. So now it's a good moment to think about prepare a proposal for us. As I said to you before, I can help with anything that you need. During November, these proposals are reviewed by the Scientific Council. They make a very deep study of the curriculum, of the people involved in the school, of the pedagogy, of the logical of the studies that you are going to give to the students, if they are well prepared, if the school is very specific, or it is very good for students that are at the beginning of their career or what. And after the following year, this is validated by the steering council. And 2 years later, you are going to celebrate this school. This is the picture of the last one. Here again, you can see Juni here. I am here too. I don't know, here works. And this is something that I think is very good for students and very good for teachers, because I think I learn a lot every time I go to one of these schools. So I encourage you to organize a school. Of course, if you want, you can write me an email and I can help you with anything that you need. And after that, I'm going to begin with my presentation about orthogonal polynomials. Well, the title of my talks was Some Properties of Orthogonal Polynomials in Two Variables. At the end, I decided to focus a little bit in some applications of, in one application that is very important, I think, of orthogonal polynomials in two variables. Sorry. So I don't know if this is something, this subject is something that you are interested in or not. So I decided to make a brief introduction about orthogonal polynomials in one variables, a little bit of history, how they appear, and what are their applications. In a second section, I will explain what's an orthogonal polynomials in two variables. I am not going to give technical properties. So the properties when we are into variables need a lot of technical definition. So I am going to go through this type of things because maybe it's not so interesting. And I'm going to focus in one type of orthogonal polynomials that are orthogonal polynomials on the unit disk, because it is better thing to see an example than many properties in general that maybe are not going to be so useful. And the last one is the application to optics. This application is related with Zernike polynomials, that orthogonal polynomials on the unities. Well, the eye is a sphere, and the behavior of the eye is like if you are in a disk or in a sphere. So if you want to study what happens in your eyes, you need to know something about the surface, something about the sphere or the disk. So I am going to explain just a little bit about optics, because I am not an expert. I am sorry if I say something that is not completely correct. I will talk about aberrations and the relation with between the optics and the mathematics, that are the Zernike polynomials. So what is an orthogonal polynomial? But if we have a sequence of polynomials of this type, Pn, where the degree of Pn is n, so we have one polynomial of degree 1, another of degree 2, and so on. These polynomials are called orthogonal with respect to a measure, mu, if the integral in the whole real line, or maybe in an interval, of the product of these two polynomials, Pn and Pm, is 0 if n and m are different, and is Hn if n and m are equal. So this is the Dirac delta. So this is equal to 1 when n and m are equal, and this is equal to 0 when n and m are different. So this means that if the degree of the polynomial is not the same, this inner product, because this is an inner product, this inner product is going to be 0, and if n and m are the same, then we are going to obtain this Hn. When this measure here is positive, then this quantity here is positive too, and then we can define the norm of the polynomial as the square root of this quantity, this positive quantity. In the case when the measure mu is absolutely continuous, then this measure is written as a weight function omega times the differential of t. So this is the weight function. I'm sorry. So if we want to study a little bit about the history of the orthogonal polynomials, we have to go back to the 18th century. And it is related with many practical problems. All these things that I'm going to talk about the history is in a work by Renato Álvarez Nodarse, is in Spanish, is Polinomios Ortogonales, Historia y Aplicaciones, is Orthogonal Polynomials, History and Applications. You could read it in English. So what were the problems? Well, in this century, it was known that the attraction between two bodies could be determined from the potential function. And this function, this potential function, was obtained by an integral of the density in the interior of the body, divided by this r that is a distance rule. So if we compute this integral, we know the potential function, and this is really going to give us the attraction between the bodies. But what is the problem here? The problem is, first, sometimes you don't know the density of the body, and even if you know it, maybe this integral is not very easy to compute. So there is another way to solve the problem, that is to solve the potential equation for points exteriors to the body. So we have here a second order partial differential equation that you have to solve to compute this potential. So many mathematicians work on this topic. For example, Bernoulli, Euler, Lagrange, all these mathematicians work in this. Legendre was interested in the problem of attraction of a sphere on a body. And in this, and when we was trying to solve this problem, he published a paper. Well, the paper was made in 1782, but it was published 3 years later. And the important thing is that in this paper, he reduces the problem to the study of the radial component of the potential. So it was a problem with 3 variables, and he reduces the problem to a problem with only 1 variable. And it's when the family of the first orthogonal polynomials appears that are called the Legendre polynomial, of course, because he was the people who invented But in this paper, he didn't prove that the polynomials were orthogonal. But 2 years later, in 1784, he proved some properties of this polynomial that appears in this problem of the attraction of the bodies. And in particular, he shows this orthogonality property. If you look at this, you can see that we have only even degree polynomials. So he only had at this moment polynomials of even degree, and he shows that these polynomials are orthogonal if the degree is not the same. And he proved also some properties about the series. The series of orthogonal polynomials are really very important in the applications. A little bit later, he introduced the polynomial of even degree that were not in the previous paper, and another polynomials that are called associated Legendre polynomials that are defined in this way by the derivative of the polynomial of degree n, multiplied by this quantity. So again, this polynomial is a polynomial of degree n. The next family which appears is the family of Fermi polynomials. He published a paper. I'm not very good reading in French. So, sur un nouveau développement en série about a new development in series of functions. This will be in English. So, in this case, Hermite, this guy here with this strange way of he studied the orthogonal polynomials with respect to this inner product. We have the integral in the whole real line of the product of these two functions, f and g, and here we have the weight function that is the exponential of minus t squared. But the interesting thing for me is that here in this paper appears to the first examples of orthogonal polynomials in two variables. And they are orthogonal with respect to this weight that we have here. So it is, here we have a positive definite quadratic form, and the exponential of this and the product of these two functions. In fact, he doesn't study only for two variables, but for many variables. And it is interesting because the polynomials in one variable were were studied a lot during a lot of years, but this didn't happen with the polynomials in 2 or 3 or several variables. So the study of polynomials in several variables is something really recent. And this is strange for me because really these polynomials appear here in this work by Hermite. So the classical orthogonal polynomials in one variable that most of the people know are the Jacobi, Laguerre, or Hermite polynomials. The Jacobi polynomials are orthogonal with respect to this weight function, 1 minus t to the alpha, 1 plus t to the beta, in the interval minus 1, 1. The Laguerre polynomial depends only on one parameter alpha. They are orthogonal with respect to this weight function in this interval, 0 plus infinity. And the Hermite polynomials that I mentioned before, they are orthogonal with respect to this weight function in the whole real line. And they satisfy many properties. Many properties. If you look at the book, for example, by Abramovich, there is a chapter devoted to these polynomials, and there are many properties that they satisfy. But there are two properties that are, I think, that are essential of these polynomials. The first is the three-term recurrence relation. So you can compute one polynomial of degree n if you know the polynomials of degree n minus 1 and n minus 2. So this is a very important relation, and there is another one that is that they satisfy a second order differential equation with polynomial coefficients. For example, the Jacobi polynomial satisfy this second order differential equation. If you look at the equation with the second derivative, we have a polynomial of degree 2. With the first derivative, we have a polynomial of degree 1. And here, this is the eigenvalue. And another important property is that in general, they can compute in a way like this. This is what we call the Rodriguez formula. So we have here the weight and we have here 1 minus t to the n and 1 plus t to the n. We are going to make the derivative n times, and after we are going to divide it by the weight. And this is going to give us an expression of the polynomial that can be computed for any degree. So one particular case of Jacobi polynomials are the Legendre polynomials. When alpha and beta are 0, then we have 1 here, and this is the Legendre polynomials, or the Chebyshev polynomials, or Gegenbauer polynomials that usually people know more about them. What are really the applications? I suppose that you have used, all of you, Gaussian quadratic rules. If you want to approximate an integral, for example, between -1 and 1 of a function f times a weight here, and you want to approximate this integral by using the evaluation of the function f in these nodes, xy, the best way of choosing this node is to look for the roots of a polynomial which is orthogonal with respect to this weight. So this is the first, I think that this is the first application that I saw, because this is something that I studied when I was studying maths a lot of years ago. And I explain this to my students now. So this is something that I think that this is the first contact that you have with the orthogonal polynomials. But there are many other applications. For example, the electrostatic equilibrium. Suppose that you have a line that is represented by the interval -1, 1, and you put a charge here and another here in the ends of the interval, and after you put inside unitary charges, negative charges there, and you let them move in the line until they reach the equilibrium. And when they are in equilibrium, these positions correspond exactly with the zeros of a Jacobi polynomial, depending on the charges that you put at the end of the interval. There are many other, for example, in quantum mechanics, in continuous fraction, in stochastic processes, in random walks, in random matrices. So there are many, many applications of the polynomials in one variable, and they have been studied for a long time. For example, to study initial value problems, they are used to, if you want to expand the solution as a combination of orthogonal polynomials, this is something that it works too. So now I'm going to move to orthogonal polynomials into variables. I am going to give the definition. I am going to show you what are really the problems that we find with them. So the inner product is defined in the same way as we did in one variable. We have the space of polynomials into variables, and we define the product of f times g as the integral in a region D of the plane of the product of these two functions, f and g, times this weight function. And a polynomial p is orthogonal with respect to this inner product if this polynomial is orthogonal to all the polynomials of lower degree. So then we are going to represent by Vn the space of orthogonal polynomials of total degree n. The difference, the main difference with the polynomials in one variable is that for one variable, this space has dimension 1. So we have only one polynomial that is independent for every degree. So if we have a sequence of polynomials, of orthogonal polynomials of degree 1, in one variable, and we have another one, the difference between one and the other is only a constant. But in this case, the space of orthogonal polynomials of total degree n is n plus 1. So we have n plus 1 independent polynomials that are orthogonal. So now it's suppose that you want to use, for example, the Gram-Schmidt process to obtain a sequence of orthogonal polynomials. Because you have an inner product, you have a space, you can order the elements of this space, and you use the Gram-Schmidt process. So you have a basis of orthogonal polynomials. The problem is that this basis depends a lot on the order that you use. For example, suppose that I say, well, I'm going to put first all the powers of the variable x, so x squared, x cubed, xn, and so on. After, I'm going to put all these powers multiplied by y, so you have y, xy, x1, y, and so on. After I multiply all these powers times y squared, this is one possibility, and I can orthogonalize this sequence. Or suppose that we think, well, no, this is, I don't like this. I prefer to order taking into account the degree of the polynomial, and after, with the same degree, I order the monomials here. So I have 1. Here we have the polynomials of degree 1, or the monomials, sorry, of degree 1. Here we have the monomials of degree 2. So I have x squared, xy, y squared. After the polynomials, the monomials of degree n, that are these. But I can interchange this. For example, I can begin with y, for example. And I have here 1, yx, y squared, xy, x squared. So I order this, and after I use the Gram-Schmidt process, and I have very different situations. So the main problem with this is that the bases that we have of orthogonal polynomials are very different. So suppose, in general, we are going to denote by Pn0, Pn1, Pn a basis of this space. So this means that all these are polynomials of degree n. So the first subindex indicates the degree, the total degree of the polynomial. So the total degree of this polynomial is n of all of them. And after, the second subindex only is a way of numerate this sequence, because we have n plus 1 polynomials. We begin from 0 to n. So these polynomials here are orthogonal to all the polynomials of lower degree, but they don't have to be orthogonal. So if they are orthogonal, then the basis is called mutually orthogonal. So if we have two elements of this sequence and the inner product of these two elements is 0, when k is different from j, so when they are different, then the basis is mutually orthogonal. If, furthermore, the product of one polynomial times itself is 1 for every k, then the basis is called an orthonormal basis. So if you think that you have only one orthonormal basis, this is not true. We have many, many orthonormal bases for the same root. So this is the main problem, or the main difference between the one variable case and the several variable case, that the basis of the space of polynomial, of orthogonal polynomials of degree n is given by n plus 1 elements. So it is a little defined. But the properties, they also satisfy a recurrence relation, where in fact two recurrence relations, one for each variable, one for s and one for y. I am not going to write it here because first I need to write all the polynomials in a vector, because this recurrence relation is a matricial recurrence relation, and I don't think that this is something very interesting. Some families that are called also classical satisfy again a second order partial differential equation with polynomial coefficients. I am going to see the example with the orthogonal polynomials on the disk. I am going to show you what is the second order partial differential equation that they satisfy. And this is very interesting because it is useful to study problems of equations in partial derivatives with some conditions about the frontier, about the border, and they are used to solve these kind of problems. So I am going to focus in one example, that are orthogonal polynomials on the unit disk. So we have this this paper by Hermite, where they appear for the first time, because Hermite really studied orthogonal polynomials on the unit disk in this paper. If you can read French, you can see here that he's going to look for the this type of function, it has a to minus phi of x, y, zeta dots, then where this function is a quadratic form, positive definite. And he's going to study orthogonal polynomials with respect to this function. So it's very interesting because it's something very, very old, and they study a lot of properties that now are being used. So what is the inner product? If we go back to the ball, in the ball we have this inner product. So we have here the product of f times g, and here we have the weight. The weight is 1 minus x squared minus y squared to mu, where this constant mu has to be greater than -1 because it has to be sense. And here we have a constant. This constant is chosen in that way that if we have here 1 and 1, so if we don't have this function, so we have the product of 1 times 1, then we obtain that the inner product of 1 times 1 is 1. So this is only a normalization constant, but the weight is this. Okay? So if mu is equal to 0, then we don't have any weight here, and we have the Lebesgue measure in the board. Then the orthogonal polynomials with respect to this inner product satisfy this second order differential equation. So this is for every orthogonal polynomials. If we have a sequence of orthogonal polynomials with respect to this inner product, they always satisfy this differential equation. Where here we have with the second derivatives, here we have polynomials of degree 2. X squared minus 1, 2xy, y squared minus 1. With the partial derivative with respect to x and y, we have a polynomial of degree 1. And here we have an eigenvalue that depends only on n. So this is something that depends only on the degree of the polynomial. And this is very important. So I'm going to show you 4 important bases that we can that we can construct. That well, they are important because they are known and they are studied and they have been used for different things. For example, there are two bases that were defined in the work by Hermite that are U and V. After we have a basis obtained by Corbinder. And there is another one that is a basis in polar coordinates, in polar coordinates that has many things to say about the optics of the eye. This is related with the Zernike polynomials. I will explain after. So, for example, this basis that was defined in the Hermite work. So we have here this U, Mn. Observe that here we have the weight, because we have 1 minus x squared minus y squared to mu, but after we have the same function here, but to m plus n. Then we take this, we compute the partial derivative m times with respect to x, n times with respect to y, and after we divide this by the weight. So this is a polynomial of degree m plus n. That's the important thing. These are polynomials of degree n plus n. So if I take all the polynomials of degree n, I can write them in this way. So here we have n minus k, and here k, and k is moving from 0 to n. This is going to give us a basis of polynomials that are not mutually orthogonal. So this means that they are orthogonal to the polynomials of lower degree, but they are not orthogonal among themselves. One important thing that is something that is almost nothing is studied about that, and it's very important. It will be very important. I am really very interested on understanding the behavior of what is the equivalent of the zeros of a polynomial in one variable. In one variable, the zeros are very important. They are used for the quadratic formula. They are used in electrostatic interpretation of the forces, or they are used in many, many things. What happens with the zeros of orthogonal polynomials in 2 or in 3 or in 4 variables? Nobody has studied almost anything about this. So I tried to plot the solutions of this equation, because now we don't have points, we have curves, lines, and these kind of things. So for example, if we look at the polynomials of degree 5, so when m plus n is equal to 5, we have 6 polynomials. And here I plot the zeros of these polynomials. If you look at this, here we have like 2 ellipses. Here we have like a flower. And again, here we have 2 ellipses in the other direction. So these are the zeros if we use this basis of orthogonal polynomials. What about the second one? The second one was in the paper by Hermite, was defined by a generatrix function. But the explicit expression of this polynomial is this, is a little bit ugly. These are Hammer symbols here and here. And here we have the monomials. But the thing is that, again, these polynomials are of degree n plus n. Again, I can have here a basis of orthogonal polynomials if I take n minus k, and k is moving from 0 to n. Then these are polynomials of degree n, and we have n plus 1, and they are independent. So this is a basis of polynomials of Pn. But again, they are not mutually orthogonal. They are not orthogonal among themselves. But they satisfy a very interesting property that it was shown by Hermite. That is that they are orthogonal to the previous basis. So if you multiply one polynomial of the basis u times one polynomial of the basis b, and this k and j are different, then this product is 0. And this is very useful to compute. For example, if you want to expand a function as a power series, as a series of polynomials of this type, this is important to compute the coefficients, these orthogonality conditions. And again, I tried to study this several times, and I didn't get anything. So if you have any idea, it could be very nice if you can say something about that. If you think about, for example, the polynomials of degree 8, here you have the zeros. You have the curves of the plane where these polynomials are equal to 0. If we have degree 8, we have 9 polynomials. And if you look at the curves, it has nothing to do with the zeros of the previous basis. Here we have lines. And here we have this kind of curves, very nice. But I don't understand really what is the behavior of these zeros. The third basis that was developed by Corbinder is like a convolution product or something like that of Jacobi polynomials. Okay, so remember that this polynomial is a Jacobi polynomial. If we have here alpha and beta, this polynomial is orthogonal with respect to this inner product, with respect to this weight. So this polynomial which appears here is a Jacobi polynomial in one variable, that is the first variable x, is of degree n minus k, but if you look at the parameters here, you can observe that the k is here. So k is moving, and it appears here. The second part, again, is another Jacobi polynomial. Here we don't have k in the parameters, these are fixed, but they are equal, this and this are equal. So here alpha and beta are exactly the same for this polynomial, and is evaluated in this quotient. So here we don't have a polynomial because we have this in the denominator. But now we multiply this polynomial times this part. So this cancels all the denominators, and at the end, the polynomial that we have is a polynomial of degree n. So this is the basis of polynomials, but they are mutually orthogonal. They are orthogonal between the polynomial Pnk and the polynomial Pnk prime are orthogonal in this case. And now the zeros. Again, we have lines, and again, we have ellipses like that. Because in this case, it's clear. We have, if we want this to be 0, or this part is 0, then we have lines, or this part is 0, and this is where we have the ellipses. the last basis, I'm sorry. The last basis is given in polar coordinates. So we have x is rho cosine of theta, y is rho cosine of theta, rho is moving from 0 to 1, and theta is moving from 0 to 2 pi. And then we have this product. We have a radial part that depends only on this rho, that is a Jacobi polynomial evaluated in this part, times rho to n minus 2j. And this is the same here and the same here. And after we are going to multiply this by the cosine and sine functions. So we have a radial part here and an angular part here. Again, the degree of the polynomial is n. They are mutually orthogonal on the space of polynomials of type n. And if we want to plot the zeros of these polynomials, we have some circles centered at the point 0, 0 that are coming from this part. And some lines passing through the origin that are coming from this cosine. So the zeros in this case are something. So the question is that the zeros depends on the basis that we are choosing. So it is very difficult to give properties about these zeros that are independent. So you have to choose a basis, and after you study the zeros. This is very, very different of what happens with one variable. So it will be really very interesting. Now we have some people who have asked us about this topic, people who are working in other topics in mathematics, or people who are working on optics too. They are asking us about this problem, and we don't know how to solve it. We don't really know how to study the general properties of the zeros, or how to compute them in a good way. And to finish, I'm going to move to the applications to optics. As I said before, I'm going to give a very simplified model. I'm going to try to explain several things just to understand the role of these Zernike polynomials on the optics. So when we talk about optics and we talk about maths at the same time, we have to talk about Zernike. Zernike was born in 1988 in Amsterdam, and his parents were teachers in mathematics. I suppose that this was important for him, but he studies mainly chemistry and also physics and mathematics, but his main studies were in chemistry. But his first university teaching was in mathematical physics. But in 1930, he turned to optics, and this is where he did the main aportations in the history. So in 1953, for example, he won the Nobel Prize in Physics for his invention of the phase contrast microscope. I'm going to speak a little bit about this microscope. Oops. So let's see something about the human eye. Well, these things about the optics are applied to the human eye or the telescopes or many other things, but I am going to focus in the eye because I think it is better to understand everything. So we have the eye, we have the diagram. In the outside of the eye, we have the cornea. Here we have a chamber filled with aqueous humor. After we have the iris here. The iris is open at the center, and this opening at the center is the pupil. And this iris is going to contract or expand depending on the external illumination, as you already. And here is the crystalline lens. It's the most important thing in what we are going to talk about. Here we have the lens. So this is like a camera or any optical system that you want to study, works in the same way. After we have a dark chamber with vitreous humor, and at the back we have the retina. This iris is connected with the optic nerve that is here. Okay, so this is the structure of the eye. I have to give a couple of definitions because, well, at least as a mathematician, I didn't know, and it is better if I say. So, what is the wavefront? The wavefront is the set of points in space reached by a wave at the same instant as the wave travels through a medium. So this is suppose that we have here the source of a wave is a point here. So this wave is moving in this direction, well, in all the direction. So this, suppose that you are, for example, in a swimming pool and you throw a piece of something in the swimming pool. So it's going to produce some waves in the water, and every wave that is going to be a circle. Every circle that you are going to provoke in the water is a wavefront. Okay, so this is the points that are reached by the wave at the same time. The medium is supposed to be homogeneous, but sometimes it isn't. Sometimes there is something that provokes that these lines are not really circles, and this is what we call the wave aberration. The wave aberration is the difference between the wavefront and the ideal wavefront. So it is expected that this wavefront is a circle, but if it is not a circle, if it is another thing that is different from a circle, then the difference between the ideal one and the one that you get is what we call the wave aberration. It's a function in two variables, and we are going to denote this function by W of x, y. So I'm going to show you a schematic representation of the wave aberration and the impact on the image quality. So suppose that we have here an eye that is aberration free. So we don't have any aberration, it's perfect. This is something that is not possible, but it's a perfect eye. Then you have here an image. The image is going to the retina. The wavefronts are perfect here. And you have a perfect image in your brain. But what happens if this wavefront is not perfect, but is a little bit modified because of different things that could be? Then these rays that are coming here, they are not arriving to one point, but you get several points here in the retina, and then the image is not very clear. Okay, so this is important. We want to understand very well the difference between the wavefront ideal, that is a sphere, that is a circle, and the wavefront that really we have. So, what is the problem with the aberration? They came from different situations. They came because of the geometry, the irregularities, the tilts, and the decentration of the components of the optical system, in our case, of our eye. And then, what do we have to do? What are the steps that we have to follow? But the first thing that we have to do is to detect the wave aberration. What is the problem? After, you have to express this aberration in a mathematical language. So what are we going to do? We are going to expand this aberration front W, this function W, in terms of a basis of polynomials. That this is where the Zernike polynomials will appear. And after, when you know what is your problem, then you have to compensate the problem using lens or glasses if it is possible, if the aberration is not too bad, or if it is worse, then you have to use refractive survey. So in the first step, we have the detection. So here we have the aberration. So I suppose you have gone to an optometrist and you have to put your head in this type of machine where you have to fix your eye or fix your sight to a point or a house or something at the back of the image, where, and after a few seconds, the optometrist knows what is happening with your eyes. What is really happening inside this machine? This is an illustration of the Harman-Schach wavefront sensor. Here you have in A an aberration-free wavefront, and in B an aberrated wavefront. So if you look at this, when the wavefront passes through the Harman-Schach sensor, the beam is broken into multiple elementary beams using this matrix of microlenses. Each microlens focuses a portion of the wavefront at its focal here in the camera. This is the camera, this is a sensor. And this forms here an array of spots. If the wavefront is flat, like this one, then the spots will be equidistant from each other. But if the wavefront is aberrated like this, then you can see what happens with the rays here. Then you can see what happened with this focus. They are not in the center. And this makes that the spots will be displaced from the focus. And we are going to have here, this is going to determine the position on every spot here. So the idea is to from this spot, to represent what is happening with the wavefront. So the first thing is that, as I said before, the eye is something that is like a sphere. So the first thing that we are going to do is to use polar coordinates. In optics, they use rho, that is the radial component, is the distance from a point to the center of the pupil. And this theta is the azimuthal angle. So they are going to measure the angle from the north. But at the end, they are using polar coordinates, even if this angle is not as usual as we are, the usual definition that we have, that is always, well, for the mathematicians, it's usually with respect to the x edge, and in this case, it's with respect to the north. So, but this is the only difference. So, what are the Wernicke polynomials, and what do they have to do with this? Wernicke polynomials are a basis of orthogonal polynomials on the unit disk. They are really a particular case of the basis that I explained before in terms of the spherical harmonics, in terms of the cosine and the sine functions. They were introduced by Wernicke in 1934 to describe the wavefront. And in 2000, that is the important thing, the Optical Society of America adopted them as the standard pattern in ophthalmic optics. So everybody uses these Wernicke polynomials to study the eye. When you go to the optometrist, they are using these Wernicke polynomials now, in this moment. And what is the definition of this polynomial? The definition of this polynomial is this. So we have here two parameters, one parameter n here and another parameter m here, that could be m or minus m. And we have two variables, rho and theta. Rho is the radial part and is between 0 and 1. And theta is the angular part, is between 0 and 2 pi. So here we have, again, a product of two things. First, a polynomial, and after, a trigonometric function, and a spherical harmonic. The thing is that the degree of this polynomial is n. If we look at this polynomial in the variables x and y, x is rho cosine, y is rho sine. If we look at this polynomial in these two variables, it's a polynomial of degree n. And this m here, that is positive or negative, is a number that is less than or equal to n, but the difference between n and m has to be an even number. and it's going to help us to enumerate the polynomials with the same total degree n. If you look for Zernike polynomials in Google, you will find many things about them and many pictures, because it's very nice, the pictures that appears about them. The radial part is a polynomial in one variable. Is this? It's a Jacobi polynomial in the radial part times this power and -1, and these polynomials are orthogonal with respect to this rho d of rho. These are orthogonal. So the radial part are orthogonal polynomials in one variable, and the angular part are again orthogonal because they are sine and cosine function. They are spherical harmonics. And as a consequence, the Zernike polynomial satisfy this orthogonality condition. I multiply this theta n with this theta n prime. And this is, if we study them in polar coordinates, they are orthogonal with respect to this weight. And if we look at them with x and y, we don't have any weight here. So they are orthogonal with respect to the Lebesgue measure in the ball. So if n and m are different, this is going to be 0. But if m and m prime, oh, this is a mistake. This has to be m prime here and m prime here. So if n and m prime and m and m prime are different, then the product is 0. And this is on the unit disk that can be represented in Cartesian coordinates like this, and in polar coordinates like this. So this is the plot of some of the polynomials. If you look at the first one, it's plain. Here we have the polynomials of degree 1. The polynomials of degree 2 are 3, 2, 0, 2, 2, and 2 minus 2. Polynomials of degree 3, we have 4, 1, 3, minus 1, and this is minus 3, another mistake. Oops. And 5 polynomials of degree 4. What are we going to do? We are going to expand the wave aberration in terms of this Zernike polynomial. So we have here many coefficients, one for each polynomial. And these coefficients here are going to give us an information about our I. So the expression of this coefficient can be computed by using the orthogonality properties of the Zernike polynomials, but in general, they are computed in an approximate way. But in fact, they could, if you know really what is this function that you don't know, then you can compute this in this way. Okay, so we have these coordinates here, these coefficients here, which are going to give us the information about the aberration. In general, these coefficients appear in an histogram of this type, where you can see that the coefficient could be positive or negative, and if the coefficient is positive or negative, it's going to give us the information about everything. The ideal thing, if the wavefront is perfect, then all these coefficients are 0. So the idea is that if one coefficient is not 0 or is very big, then it's because we have a problem here. This histogram in general is rescaled because you can read them in terms of diopters, positive or negative. For example, the polynomials of degree 1 are going to give us the vertical and the horizontal tilt, but the most known are these, the polynomials of degree 2, that are going to give us the astigmatines. Here, these two polynomials are going to give us, if we have astigmatines, and this is going to give us the default. So if we have myopia, if the coefficient is positive, or hyperopia, if the coefficient here is negative. This, until this part, we have the lower aberrations, but from here down, then the problem is bigger. So until here, we can solve this with lens, glasses, but from here down, then we need surgery because we have coma or trefoil or any other problems more serious. So here, only for you to look at the polynomials, to see that they are really polynomials, I wrote all of them, well, all of them until degree 3. You see here the polynomials of degree 1 are x and y, so it's very simple. Here we have the polynomials of degree 2 in Cartesian coordinates and in polar coordinates. And as I said before, this is going to give us, if the coefficient corresponding to this polynomial is big, then we have a problem of astigmatism in this case too, but the degree is different in this case or in this case. And here, if the coefficient is positive, we have myopia, and if it is negative, we have hyperopia. And these are the most serious cases. Okay, and that's all what I want to say. I want to finish with this picture of the last SIMPA school, where here is Kiki and here myself together in the picture of the professors that were participating at this school. So thanks a lot for inviting me and for staying here for this presentation. Thanks.
Okay, thank you very much, Professor Lidia. It's very interesting talk. So right now it's time for question and answer. We don't have question in the chat, so might be the participant would like to ask Professor Lidia. Could you please raise your hand? You can ask about the orthogonal polynomial or about SIMPA. It's up to you. Any question? Okay, before maybe the question will be it's quite hard to ask. I'm interested in the pictures because I'm not familiar with the work in here. The picture of the function in zero. So I see there is always what you call it? It's like a symmetry, but it has to be rotate 90 degrees. About would you like to back of the maybe in the zeros? I think you have two pictures with zeros.
So here, for example, we have
one example, yeah, because this is you have 6 even, yeah. So it looks like the first row, it's the same with the second row, just make a rotation 90 degrees. But in the others, it's not like that, but it's line and something. Yeah. So, oh, sorry, this is also the same. So is this always the pattern of the zeros?
But there is this, for example, doesn't happen. If you look at this, so, for example, this
that is different, right? There is no similar pattern.
That's the point. The point is that I can't find a pattern in general. I cannot find a pattern. I don't know why. In fact, I was trying, because of the application to the stochastic processes, I need to find a point in the disk where no polynomial is going to be 0, and I cannot find.
Okay. So
because there is always a polynomial who is going to be 0 at this point. If you choose any point on the disk, there is always a polynomial who is going to be 0. Yeah, and it doesn't matter what kind of basis do you use. So I cannot find anything.
If we have different bases to to work in this polynomial, do we have different zeros in here?
Yeah, that's the point. So you have the same weight, but different zeros. So if you use the basis of this, you have these zeros, and they are not symmetric, and they don't satisfy. I don't know why, and they are out of the disk. But if you go back, for example, the first basis, all the zeros are inside the disk, but these lines, vertical lines that are the axis, 0 and the y-axis and the x-axis, and all the other zeros are inside the disk. But this only happens in the spaces. If you change to another one, It's completely different. So
Okay.
I cannot find a pattern with this. Somebody told me that probably with these polynomials, well, I don't know, because I always ask these type of things, but with these same polar coordinates, maybe it was a torus that was intersecting the plane twice or something like that, but I don't see. I don't have the ability to understand.
So there is no like properties that if the properties like this, we have like nice zeros or something. So it depends on the basis and also in the weight.
I don't know, but it's very strange because for the polynomials in one variable, for example, if you look at the polynomial of degree n, you have the zeros. And you look at the polynomial of degree m-1, and they are interlacing with them. So they have a lot of behavior that is very nice and very funny. And here we don't find anything. So I suppose that we are doing something wrong, but I don't know. We are not looking at the good
we
direction.
haven't found it yet. So when we want to learn about the orthogonal polynomial, and I know that we can like have like several inner product, I think. So you use the integral. If like we work in, I don't know, it's like easier or simpler with the sigma. Is there any some overlapping properties, or it's completely different if we choose?
In which case, sorry?
Like the inner product. So when you call it orthogonal, it's like there is a product that it's equal to 0. If we use different, if we use different product,
another product, well, in the disk, everybody uses this because it's symmetric and it satisfies well, because the weight is good in this. But if you change the region, for example, in a triangle, you can use similar bases and you have another properties different. Or if you use, for example, the Hermite polynomials that are defined in the whole plane, you have another situation and the behavior is different. So it's something strange for me. So I always talk a little bit about that because I think that sometimes I will find somebody who knows something more than me and is going to give me a clue or something. I cannot hear you, Kiki. I think that you mute yourself.
There is a sound from outside. So it's very interesting. So there is like lots of mystery in this problem that we can work in the future, maybe.
Yeah, and it's easy to understand, I think, no? So the problem is to understand. You have an inner product, you have a basis for this polynomials that are orthogonal, and you want to understand what happens with the zeros. You can be studying geometry or algebra or analysis, and you can try to find something.
Okay. So I think this is a nice problem for the next research. We have Bu Yuni from UGM. Hello, Bu Yuni. How are you doing? So maybe you want to say
Lydia.
hi to Lidia.
Hi, Yuni.
Hello.
How are you?
Hello. I'm sorry, I'm a bit late to join because it's together with the. So, how are you?
Fine, and you?
Fine. Okay.
So thank you for
It's
joining with us.
surprising that you give a talk in UI because when I got the flyer, oh, Lydia. Yeah.
So that's why I sent it to UGM.
Yeah.
Okay, so
Nice
we also
flyer.
like have the farthest is Dr. Atmi. You have any question, Patmi, or comments? Patmi is from Andalas, is from Sumatra, yeah, other island. Ibu Putri, Bu Rahmi, Pak Dipo. Do you have any question or comments, or Pak Alhadi maybe?
It's very specific.
Yeah. Yeah. So
Okay.
yeah. Yeah, they're like hopefully like your talk will give us like some inspiration about there are like more stories in the polynomial that might be we learn polynomial in the undergraduate or graduate
There is
program,
another
but yeah.
thing that there is another thing that is important, that now everybody uses these Zernike polynomials to study what happens in the eye.
Okay.
But is this the best? Or maybe there are things that could be work better? Because, for example, you have problems. Well, as far as I know, because I have some colleagues that work on this topic, that, for example, if your problem is not in the center, but if it's more in the outside of the disk, let's say, the sensor is not working so good, and the polynomials are not working so good. So it would be interesting to find another polynomials that probably, or polynomials or functions that could be work better. This is an important problem to solve, I think. Okay. Because this is not the last, this is something that has a lot of years, so maybe there is something better.
So theoretically speaking, we can like have an opportunity to find other kind of polynomial that is orthogonal and can model about like some problems and have the better result.
Yeah, because well, we are talking only about the monochromatic aberrations, but after there are another type of aberrations that they are not covered really well with the Zernike polynomials, and probably there is something better. So this is why I think that it's important. But well, now this is something that is very interesting because it's what they use now in this moment. So it is interesting to understand. Also, in optics, you know that people in the enterprises don't share the things that they are using a lot.
It's a secret. Okay, so anyone wants to? Yeah, there is one question, Harina from Unipa. I need to read it because it's quite okay. Mbak Harina, do you like to talk directly to Lidia, or it's better I just read it? So she asks if you can give some cases of Zernike polynomial related with basis orthogonal and matrix transition.
Sorry?
If you can give some cases of Zernike polynomial related with basis orthogonal and matrix transition.
Matrix
or matrix, Harina?
Matrix transition.
Matrix. Okay, matrix transition.
But matrix, what do you mean with matrix transition?
If we have two different bases, if we have two different bases, and how to find the matrix transition related to
from one basis to the other, you mean?
Yeah.
Well, the usual thing is using the orthogonality, but it's the only way. I think, for example, if you have a basis like that, and if you have two different bases, and you know that they are both orthogonal, then the first thing is that, for example, if one polynomial is of degree 1, it has to be expressed as a linear combination of the polynomials of degree 1 and the polynomial of degree 0. Once you have that, you multiply it by one of them. So in the same way as you compute, let's see if I can explain it. In the same way as you compute these coefficients in this way, if here you have, suppose that here you have a polynomial of degree 1, okay? So if this is a polynomial of degree 1, then the expansion finishes here. This part doesn't appear. So you have only this. And now to compute these polynomials, or to compute these coefficients, you only have to multiply this polynomial that you have here times one of them and divide it by the norm. So this is going to give you the transition matrix. That is what you mean, no? Do you understand what I say, or do you want me to take something to write? I don't know if you understand. I am going to repeat it. Suppose that here you have a polynomial of degree 2. Okay, if you have a polynomial of degree 2 that is from another basis different from the Zernike basis and is of degree 2, then it is going to be expanded in terms of Zernike polynomials until the third row, because you have the polynomial of degree 0, 1, and 2. And this part, this lower part, is not here. So we finish here. And now we need to compute these coefficients. How do you compute these coefficients? By using this.
Okay.
In the denominator, we have the norm of the Zernike polynomials. This is an integral that you can compute with some kind of program that you use. And here you multiply the new polynomial that you have times the corresponding Zernike polynomials. If you want to compute this A00, then here you have to write zeta 00, and here the norm of zeta 00, that is 1. And this is going to give you this coefficient, and so on. So this is the transition matrix. Do you understand what I mean?
Thank you. Yes. Okay, thank you.
You're welcome. We don't hear you, Kiki, again. You are muted.
Sorry. Any other question and comments? Pak Dipo, lagi rapat nggak?
Okay. Thank you.
Okay.
Yeah. Thank you very much, Lidia. I have to say sorry because I have to follow your presentation pretty late because I have to parallel with meetings. So I just follow your presentation in the last part about the implementation of these polynomials. So correct me if I'm wrong, because yeah. So with this polynomial, you can detect that someone's eye retina have problems or not. That means that after you map, you do the mapping of someone's eyes, yeah, and then you detect about is this need like a treatment or not. Is the mapping result is always like you have a limited result of mapping, or if you find something new, then what will you do? You categorize it as a health retina or have a problem, something like that.
Sorry, I didn't understand the last part.
Yeah,
so
I mean,
you have this. I'm going back. You have this system.
Yeah.
That is going to give you an array of spots.
Yes.
If the wavefront is fine, then these are X-passed, and if it is not, they are displaced from the place that they should stay.
Okay.
So the thing is that with these points that you have, you can imagine somehow how is the wavefront.
Oh, I see.
So it's an approximation, really, because it's not something that you don't know exactly the wavefront, but it's an approximation. It's a good approximation because it's what they use now. So this is what they are using in optics to study if you have myopia, for example, or something, or astigmatism.
I see. So detecting about the type of the problem that the patients faces, it's in another level. I mean, like maybe for
I don't hear you very well. I don't know if it's a problem of my phone or maybe could you speak a little bit?
Speak a little bit.
I don't understand you very well. I'm sorry.
Yeah. Sorry. This first.
I am going to.
Yeah. Can you hear me clearly now?
Yeah, I think so. Because...
Okay. Yeah. Good. So with these methods that we can detect a problem that in the eye of someone, yeah, something like that, which is can be seen with the red dots in the part B of your figure. So it means that when someone, you say that, okay, this result is show that the patient has a problem which needs medical treatment as soon as possible. But the type of the problem, for example, like is it a retina problem or something others, which is not categorized in this from this result. Is it true or maybe?
Oh, well, it is,
yeah, the
many of
categories.
them are categorized. I'm going to show
Oh, okay.
you. Well, you span the wave function, the wave aberration in terms of these polynomials. And you have these coefficients. When you look at these coefficients, if one of them is very big, like this, then it means something. And depending on which one is the one that is big, then you can say something about. So for example, if it is the second, if you are in this row in the second degree, then you have astigmatism, or you have, depending, for example, the defocus. If the coefficient corresponding with the polynomial theta 2, 0, if this is positive, this means that you have myopia. If this coefficient is negative, this means that you are hyperopia.
I see.
For example.
I see.
So this is very well solved with the glasses, but if you go to the following row, then you have coma, for example, or these are more problematic problems. You have to go to the surgery to solve them. So this is going to, these coefficients gave you the information about what kind of problem do you have. So this is why they are so important.
Okay. So the coefficient is the one of the most important from the result, which we have to identify them. Okay.
Yeah.
Okay. So thank you. It's
this is the way they see. This is the way they see with an histogram, so they can see. But in general, they are in dioptries, so they know that you have 3 dioptries in myopia, or you have some problem with astigmatism because they have here the numbers.
Okay. Yeah. Thank you very much for the explanation. It's very clear.
Very interesting. So Pak Dipo is like our research coordinator, research manager, not coordinator, research manager of our faculty.
Yes.
Okay.
Thank you so much for your question.
Other comments or question? Is there any question about SIMPA? So if like you like to do the SIMPA school, hopefully next year it's already safe for travel.
Juni, are you going to organize a school?
Juni?
I put a picture of Juni. I am going to show her.
Oh, thank you. Which one? Yeah.
Have you seen this?
Yeah. Okay. You should come again, Lidia.
Yeah,
we are preparing a SIMPA proposal this by October, yeah, the last one. But still, it's relating with coding. So you should come again, Lidia, in 2000 and
of course. But now, you are preparing for this time, that is for 2024?
For next year,
2023, yeah? 2024.
2024.
Yeah.
Because 2024, for 2023, there is nothing.
Yeah, it's already over, the application. Okay. And
it's until October.
Yeah.
You have
and
time.
Then the proposal, the deadline will be October
this year.
Yeah,
October 9, I think.
But we would like to do as following, Lidia. So for 2023, we propose for same school. This is a like preliminary for the Chimpa school. So, but
I know.
I only give direction. Not me propose preparing the proposal. My colleague in the department under direction of Indah and me will propose this. So let's see if they can do this on time.
So,
Because
let's hope. Let's
yeah.
hope.
Yeah.
so the
This
same
is for
school
this
is
year, for 2023, is the same school.
Yeah. For 2023 is for the Siam school.
For the Siam.
And the topic is a kind of preliminary for the Simpa one. Like the objective of the Sim school is for preparing our student for doing the next Simpa. Yeah.
Oh, perfect. Perfect.
Yeah.
Look, this
Yeah,
school was really well prepared and well organized. It's very, very good. That's true.
Yeah.
Not always it's the same. It was very good. Yes, it's true.
Yeah. I told to the guy who will prepare this proposal that you, after you got the maybe a bit information for the preparing this, then you can contact Lidia.
Yes,
And then
sure.
And he will contact you. I think he will contact you soon. Yeah.
Perfect.
okay.
I can help with anything.
Yeah, so UGM already like preparing for the application. How's about the UI team? You already met Lidia. So
yeah. We expect maybe for this 2024 maybe one more Cimpa in Indonesia ya. Ya Bu. Bu Kiki bikin SIM school-nya terus nanti diikuti Cimpanya. So
ya ini lagi
for preparing.
waiting for my other colleagues to
Bu Kiki.
Pak Dipo.
Yeah, if it is possible, then why not? From the faculty level, I believe that we will really support if mathematics want to do this. I'm as a part of mathematics, I really appreciate that if we can initiate this in mathematics before in Gajah Mada. So yeah, I believe. So
maybe Pak Dipo, so maybe a bit complementary topic, so maybe it would be good for maybe we can discuss with our people. This is Mr. Uha prepare this. You know him? I can talk to Uha. I can tell Uha that UI would like also to propose, and then maybe the topic is maybe a bit complementary, so we'll reach the development of this mathematical activity supported by Cimpa. Because Lidia, we have our university maybe the same with UI, with using the grant of world class university that we support such activity, so to make our student more engagement with the foreign topic.
But don't you have somebody who are you talking to in Europe or what? Or you mean which university there in Indonesia? What do you?
We have the grant for inviting professor from overseas.
So you have a professor who you are talking to or what?
Actually, we in Indonesia, at least this last 2 years, it's already, they have a program from the ministry that world-class professor, which means that every university in Indonesia can invite overseas professors to come to Indonesia and give like a workshop, tuning for the article, collaboration for publishing papers, and workshop for the students. And I
this
believe
is very,
that
you can use also the SIMPA courses for this. If you, for example, want to organize a school in 2024, you can invite in 2023, you can invite a professor to give a course to the students, and this is going to be covered in somehow with SIMPA. So then I what I don't know if I understand the question with, because you are going to organize you are thinking about organizing two schools that is really very good. One in one university and one in the other. And you want them to be complementary. That's the point, no?
Yes, yes, that's the point.
But you have, I don't know if you have talked to some people in, I don't know, in Germany or in Spain or in France to organize the school with you, or you are looking for these people too?
I think that we are looking for.
You are looking for.
We are looking for.
That's the point. Then this is something that is not there in these slides that I share with you. But the thing is that I can help with that. If you say, well, I want to organize a school about.
Okay.
I don't know.
Yeah.
Lidia, what do you think? Do you know somebody who could be interested in this topic? And I can try to put these people in contact with you so that you can see if this is compatible and this is possible. You can do that. We can do that.
Okay. Okay. Good.
So you have to ask, because it's the best way to solve all this type of problems. So you can write.
Maybe I talk to you, Lidia and Tipo, the following. So I think some months ago, Lidia, I sent you an email. I talked that we would like to organize a SIMPA school, and then experience from the last one, we have to have a partner in Europe, maybe in France or in Spain or in and then Lidia suggests me to you decide. We should decide which topic we would like to do, and then if we couldn't find by ourselves the partner, Lidia can help.
Yeah, that's the point.
Is right?
So or maybe you have the partner and you don't know what kind of a school you want to do, and then you can think about. But if you don't have the partner and you want me to help, I need to know more or less about what is the school, because there are many people
the topic
in the world. So I need to know the topic of the school, of course. If you tell me what topic is that you are interested in, I can find somebody for sure.
And maybe for preliminary information, I'm not really fixed with this. Is about in Jogja is about relating with number theory. And then they already discussed a bit about possibility to invite Francisco Papalardi, Lidia, maybe
Francisco Papalardi is
So maybe this guy, Mr. Uha, will contact you and contact him, and then maybe talking about maybe if you have any suggestion before preparing the proposal, maybe to write down maybe suggestion relating with the topic. Number theory is very broad, but maybe which number theory, in which direction is number theory we would like to do. So because this is a field that we feel we are very not very good. Need more improvement. I mean, we need more improvement in this area.
Okay.
So maybe this people.
Have you talked with Francesco Papalardi or not? Did you talk with him or not?
I don't know, because on the last meeting last week, before Mrs. Indah going to Turkey, and because the initiation is the following. So Indah, as a president of Indonesian Math Society, is informing about the possibility to prepare sim school, sim school. And then we talk about this, and then I also suggest choose a topic of sim school that maybe will very good to prepare our student to join the MIPA school that we would like to organize. And then we discuss which area is. And then no, we prepare about the sim school first. And then one of the possibility is to contact Francisco. And then Uha sometime already have already make a contact with him for talking about the last meeting here in Indonesia for MIPA with you, Lidia. So I think Uha make a good contact with him, but I don't know if he already talking about this MIPA topic with him. Yeah. So
well, if he's going to join you with the SIAMS school. Francesco is going to be in the SIAMS school or not?
He already on the list that he's possible. So because we make a list first, we make a possible list first. So
and you talk to him about this.
Yeah,
I think that he's very involved in all these type of things. I think that he could be a good contact. I think if you want, I can talk to him, but I think that he's going to be delighted with the idea. I don't think there's any problem, and he's going to prepare a good proposition. I think so.
So Dipo. So
yes.
This might be give you an idea. If in UKM is relating with the number theory, maybe you complementary thing. So to make maybe more to application or more to computation, or maybe this is the possible, the good thing that so we could make a cooperation relating with the development of math in Indonesia through the MIPA.
Yes.
And Lidia, in our university also still offering some support from university for organizing such international school like the last one. Remember, we use this money for helping some student from who cannot got the support from MIPA, for example, so they can stay. Everybody can stay in the residence. You remember? So this is one of this.
It was very good. Yeah.
Okay.
I hope I hope in 2024 university still give this scheme.
Yes.
It's great because sometimes it's like changing to other form.
Yeah,
we cannot use it anymore.
Yeah,
for us it's the same.
Yeah,
for us it's the same. In Spain, 1 year you have, the next year you don't have. So
okay, then I think this time we have like really have like enrich our knowledge about the not only for the MIPA, but also like for the orthogonal polynomial. And this is like a new area, I think, in Indonesia. So might be like in the next future, there is someone who like to like do the research in this topic, or maybe in a MIPA school for I don't know in which year. Okay, so thank you very much, Lidia, for
thank you for
attending.
Lidia, thank you very much for the duo.
And
for the duo for photo.
Yeah, thank you, Bu Yuni,
very nice.
And the others, Pak Admi.
Terima kasih semuanya ya. Saya ikut-ikutan nggak ngerti isinya.
Thank you very much, Bu.
You give us like we can learn from Gajah Mada University how to like make the workshop or school international school. Okay, so Pak Dipo, do you like to give some comments for closing this event?
Yeah, thank you very much, Bu Kiki. So once again, Lidia, I really appreciate your time, to share your knowledge, and this is very nice. Especially, I believe that our students in the undergraduate, they should see this, because some problems for the undergraduates, they sometimes asking about what should I do with this polynomial? What can I do if I integrate, differentiate, and something more more advanced mathematics? What is the application? That's something which is really difficult to give interpretation for them in the first or second year student. But yeah, so once again, thank you very much. I'm sorry I cannot join your talk from the beginning, and I hope what Bu Yuni say before, that we can maybe Pak Alhadi as a head of the Department of Mathematics we can discuss this, Pak Alhadi, about who knows that we can help on international schools before CIMPA in UGM, so we can complementary with the topics. Okay, so thank you very much again, and I hope to see you again, Lidia, in the future. So thank you.
Let's join me to give a big applause for Lidia.
Thank you.
Thank you, Lidia.
Thank you so much for your invitation.
Yeah, thank you. So dikembalikan ke Bu Yustin, Mbak Yustin ya? Yustin?
Bisa ditutup aja sama Bu Kiki, Pak. Silakan.
Oh, okay.
Okay. So I think this is the end of our MIPA talk. Once again, thank you very much for Lidia, for Pak Dipo, and for all the participants here from UGM, from UNAN, and Universitas Jember. I don't remember all the names, but and also colleagues of Department of Mathematics UI. Hopefully this talk will give us more knowledge and insight about what's the next research, or also for use the information of SIMPA for going to hold the international school in the future. So thank you very much. Have a good morning for Lidia and good afternoon for us.
Yeah.
Thank you.
Thank you very much. Have a nice weekend.
Nice weekend.
Have a nice weekend.
Thank you, Lidia.
Bye. Yeah.
Thank you. Bye.
Thank you.
Thank you. Bye.
Okay, so bye from now.
Bye.
So see you again.
Yeah.
Everyone.
See you soon, I hope.
Yeah.
Yeah. You should come again to Jogja. Yeah.
Yeah. So
bye.
Bye now.
Terima kasih Bu Kiki.
Iya, sama-sama.
Terima kasih ya Pak Alhadi, Bu Kiki, Mas Dipo.
Sama-sama Bu Yuni,
Ya.
jadi nambah wawasan.
Terima kasih Ibu.
Sama-sama. Udah ya